Hello friends, nice to meet you. Today we are discussing about certain models related with time series. As you know, time series has several components like trend, seasonal, cyclic and random effects. First of all, we will study how to separate these components. Then we will talk about additive as well as multiplicative model in detail. Similarly, we shall also talk about the stationary time series, and then we want to know how we can detect stationarity in a given time series. There are certain tests which we shall study here in detail. So, we can start our lecture.
Today, let us understand time series models. What is time series? It is a series which relates the given observations pertaining to certain phenomena expressing the variation according to time. For example, series of observations for production, sales, share price, atmospheric data, rainfall, consumption, income saving, etc. during successive years or months or weeks or quarters or days. Study of such series is important in the sense that if we can examine the pattern of variation or some systematic modeling approach, then it can be made useful for further planning exercises. Hence, such a study has its own importance for government agency as well as corporate houses, businessmen and etc. What are the components of a time series? If we closely examine any given time series, then we can find the existence of the components of time series data, and they are: number 1, trend component. The variation or changes that occur during some longer span period is called trend component of time series. These are the fluctuations which exhibit not in shorter period, but in some longer period, and they reasonably affect the given time series. For example, price of commodity during 3 to 5 years period, demand for two-wheelers in some years, sales and purchases of electronic items during successive years, etc. Here we find that such a variation is found not in shorter period but for a longer period. These changes are attributed due to aptitude, fashion, habits, living standard, financial status of people, etc. Trend component exhibits long-term variation in the given time series. It is also the most prominent part in the given time series. Second component, seasonal component. Demand for raincoats in monsoon, demand for woolen clothes in winter, prices and demand for medicines during season which cause infection, fever and other casualties, number of passengers during festival days, etc. These are some examples how the variation are observed during seasons or quarters or weeks. These are short term fluctuations in the given series. Number 3, cyclic component. There are business cycles which exhibit changes in the observations over a certain period. These are regular changes, but they are not short term changes. If we examine the series over a longer span period, cyclic fluctuations can be seen to have short term variations. Number 4, irregular or random component. These changes occur due to accidental circumstances, for example, flood, famine, frost, earthquake, fire, accidents, etc., which are random events and they can cause variation in the given time series. Generally, these variations are not in our control as they occur at any time and can affect the data reasonably. If we summarize all the above factors, then given time series for its additive model can be expressed as composed of time series equal to trend plus seasonal plus cyclic plus random. Thus, Ts equal to trend for T, S seasonal plus C cyclic plus R random. Number 3, how to separate the component of time series. Methods to separate trend component. Number 1, graphical method. If we plot the given time series observations against time, we can examine the variational pattern of the series from the graph. For example, it can be linear or quadratic or curvilinear, etc. This is an approximate method which can give us first hand information about general pattern of the series. Number 2, moving average method. This is a very simple and useful method to obtain trend component of the time series. It is based upon taking successive average obtained from the observations according to periodicity of the series. If we plot the observations against time, then the average of the periods for highest or lowest fluctuations can determine the periodicity, which can be 2 or 3 or 4 or 5 periods, etc. If the periodicity is 3 years, odd years, then we first find sum y1 plus y2 plus y3 and divide it by 3. Place it against second observation. Then take next y2, y3 plus y4 and divide it by 3 and place it against third observation, and so on. If the periodicity is 4 years, even years, we first find sum y1 plus y2 plus y3 plus y4. Place it between second and third observation. Then sum two consecutive values and divide the sum by 8 and place it, and so on. We lose some observations at the top and in the bottom while doing so. We illustrate this by two examples. Let us understand example number 1. Here you can see time and observation is given and we have to find periodicity for 3 years, which is odd year. So, first we do sum of 3 observation, 10 plus 12 plus 16, which is 38, and we place it against the time 2. Then 38 divided by 3, which is equal to 12.67, and so on. Example number 2. Here time and observations are given and here our periodicity is for period 4, that is even period. So, first we do sum of 4 observations, 12 plus 17 plus 21 plus 23, and place it between 2 and 3, which is 73. Then again we take sum of another 4 observation and we place it against 3 and 4. Then we find sum of 2 observation, which is 73 plus 80 and divide it by 8, which is 153 by 8, and that gives answer 19.1, which is our trend value, and so on. Similarly, we can find the trend for all the observations. It may be noted that moving average obtained to find trend is in a way weighted average of the successive observations. Number 3. Iterated moving average method. This refers to the above note that moving average is in a way a weighted average. If we use moving average method for more than one time, then it is an iterated moving average. Here there are different methods given as per the period for weighted average. Some are known as Spencer's 15-point formula, Spencer's 21-point formula, and etc. Number 4. Least squares method. Suppose that given time series has its trend given by yt equal to beta 0 plus beta 1 t plus beta 2 t square plus up to so on beta p t raised to p plus ut, where t follows 1, 2 up to n. We can obtain beta coefficient by minimizing the residual sum of squares. These are OLSE of betas. On substitution of beta coefficients, we can estimate polynomial trend given by yt cap equal to beta 0 cap plus beta 1 cap t plus beta 2 cap t square plus up to so on plus beta p cap t raised to p, where t equal to 1 to up to n. Let us understand it with the example. How to fit polynomial trend? Yt equal to a plus bt plus ct square plus ut. We write normal equations by minimizing error sum of squares. Summation yt equal to na plus b sigma t plus c sigma t square. Summation tyt equal to a sigma t plus b sigma t square plus c sigma t cube, and summation t square yt equal to a sigma t square plus b sigma t cube plus c sigma t 4. Hence, yt cap equal to a cap plus b cap t plus c cap t square, which is estimated trend. Number 5. Variate difference method. When we assume a polynomial equation in time of degree p, we do not know what will be the value of p. This is accomplished by variate difference method by means of a t statistic. Thus, whether the polynomial equation in t is of second or third higher degree, this method determines it, and then trend can be estimated. Number 6. By fitting growth curve models. Some growth models like Gompertz, modified Gompertz, logistic curve, etc. can be fitted for trend component assuming functional relationships for trend equation. Gompertz curve, that is log yt equal to a0 plus b0 multiplied by r raised to t, and logistic curve is given by yt equal to k upon 1 plus b exponential minus at. Here different methods are used for fitting the above curves to the data. Methods for determining seasonal component. Number 1. Moving average method. Given time series can be expressed in its additive form by yt equal to t plus s plus r. When we apply moving average method to determine trend, then subtract estimated trend t cap from the series, so that we get yt dash equal to s plus r, which consists of seasonal and random component. Now again apply moving average method for each year, quarter wise or season wise. For example, for 4 quarters it is moving average with periodicity 4. This will eliminate random component and we get seasonal component s. We can find quarter wise or season wise average to express respective seasonal component. Number 2. Method of seasonal index. Suppose that given time series has observations for 5 years and for each of 12 months in an year. We express these observations by Yij, I equal to 1, 2 up to 12 and j equal to 1, 2, 3, 4, 5. First, we compute monthly average, that is Ai equal to summation j from 1 to 5 Yij by 5. Next, find overall mean, A bar equal to summation j equal to 1 to 12 Ai divided by 12. Now, compute seasonal index Ii equal to Ai divided by A bar multiplied by 100. We set the series which is separated from seasonal index by Xij, which is equal to Yij upon Ii multiplied by 100. This contains t plus r components. Then we can obtain seasonal index from Sij equal to Yij minus Xij, that is S equal to t plus s plus r minus t plus r. Note, there are also other methods like A. Method of link relatives, B. Ratio to trend method, C. Ratio to moving average method, and etc. How to separate random component? When other component are estimated, the remaining part is the random component. Thus, given time series yt equal to t plus s plus r, yt dash equal to yt minus t equal to s plus r, yt double dash equal to yt dash minus s equal to r, which is equal to random component. Note, in the presence of cyclic component also we can separate cyclic component in a way similar to trend component in general, and then step by step we can obtain random component by elimination procedure. Number 4. Multiplicative model for time series. Many times we can observe that not additive but multiplicative model for time series is useful. We express additive model by yt equal to trend plus seasonal variation plus cyclical plus random, that is yt equal to t plus c plus s plus r. If we include all the 4 above components, then multiplicative model can be written by Ts equal to yt equal to t multiplied by c multiplied by s multiplied by r. A speciality of this model is that if a component is not present, we take it as 1. For example, if s is absent, put s equal to 1, then yt equal to tcr. Similarly, if c is absent, put c equal to 1, then yt equal to tsr. Such presentation of multiplicative form is useful for very long time series. Generally, when the variational part in the series is of exponential type, multiplicative model may be useful. The respective component can be obtained by division rather than subtraction in the case of additive model. For example, yt upon s equal to t multiplied by r, yt upon t equal to s multiplied by r, etc. It may be noted that our discussion up till now refers to non-stationary time series models. Now we shall discuss stationary time series and relevant results step by step in brief. Number 5. Stationary time series. In a stationary time series, there are no components like trend, cyclic or seasonal factors. Such time series is in relation to stochastic process and hence they have very wide applications. Certain statistical events which are connected with time and follow laws of probability exhibit stochastic process. Example: number of passengers traveling by air day to day, temperature record at some place for different days, number of absent employees in a production unit at different days, etc. These events are linked with certain probability laws. Definition of stationary stochastic process. A stochastic process is said to be stationary if its mean and variance are constant over time and the value of the covariance between the two time periods depends only on the distance or gap or lag between the two time periods and not the actual time at which the covariance is computed. Let yt be a stochastic time series with the properties mean equal to expected yt equal to mu and variance equal to expected yt minus mu square equal to sigma square. Covariance equal to gamma k equal to expected yt minus mu multiplied by yt plus k minus mu, where gamma k, the covariance at lag k, is the covariance between the values yt and yt plus k, that is between two values of y at k periods apart. If k equal to 0, gamma k equal to gamma 0 equal to sigma square. If k equal to 1, gamma 1 is the covariance between two adjacent values of y. From this, we understand that if a time series is stationary, its mean, variance and autocovariance at different lags remain the same no matter at what point we measure them. Thus, a stationary time series is time invariant. From this, we may also understand that a time series is non-stationary if it is not time invariant in the sense that it will have a time varying mean or a time varying variance or both. Purely random or white noise process. We call a stochastic process purely random if it has 0 mean, constant variance and it is serially uncorrelated. In classical linear regression model, we assume that UT follows independent identical distributed normal with mean 0 and variance sigma square. That is, UT is independently and identically distributed as normal distribution with 0 mean and constant variance. Such a process is also known as Gaussian white noise process. Random walk model. It is often said that asset prices such as stock prices or exchange rates follow a random walk, that is, they are non-stationary. For example, today's stock price is equal to yesterday's stock price plus a random stock. We have two types of random walks. Number 1, random walk without drift. Number 2, random walk with drift. Let us understand random walk without drift. Let UT be a white noise error term with mean 0 and variance sigma square. Then the series yt is said to be a random walk if yt equal to yt minus 1 plus ut. We denote it as equation number 1. This is also called AR1 model. From equation number 1, y1 equal to y0 plus u1, y2 equal to y1 plus u2, which is equal to y0 plus u1 plus u2 and so on. Hence, we get yt equal to y0 plus summation ut. We denote it as equation number 2. Expected yt equal to y0 and variance of yt equal to t sigma square. Here, as t increases, variance increases indefinitely. Thus, RWM without drift is a non-stationary stochastic process. If we write equation 1 as yt minus 1 equal to ut, which implies delta ut equal to ut. It can be verified easily that while yt is non-stationary, delta yt is stationary. random walk with drift. We write yt equal to delta plus yt minus 1 plus ut. We denote it as equation number 1, where delta is called drift parameter. We have expected yt equal to y0 plus t multiplied by delta and variance of t equal to t sigma square. We denote it as equation number 2. Here delta yt equal to yt minus 1, which is equal to delta plus ut. We denote it as equation number 3. This shows that yt drifts upward or downwards depending upon delta being positive or negative. This model is also called AR1 model. Autocorrelation function and correlogram. It is important to know whether the given time series is stationary or not. A simple test for stationary is based upon autocorrelation function we defined as ACF. ACF at lag k is defined as rho k equal to gamma k upon gamma 0, where gamma k equal to expected value of yt minus mu multiplied by yt plus k minus mu, which is equal to covariance at lag k and gamma 0, which gives sigma square. The autocorrelation function defined above has the properties: number 1, rho k equal to rho minus k; number 2, modulus of rho k less than or equal to 1; number 3, rho 0 equal to 1. In order that we can decide about an appropriate model for given time series, ACF will be useful. Generally, we do not have value of rho k based upon population. Hence, we estimate rho k from the sample. If values of rho k are plotted against k, it is called population correlogram. We can obtain estimates of gamma k and gamma 0 based upon samples which are gamma k cap, which is equal to summation yt minus y bar multiplied by yt plus k minus y bar whole divided by n, and gamma 0 cap equal to summation yt minus y bar square divided by n. This gives sample autocorrelation function given by rho k cap equal to rk, which is equal to summation yt minus y bar multiplied by yt plus k minus y bar, which is divided by summation yt minus y bar square. When we plot the value of rk against k, we get sample correlogram. Usefulness of sample correlogram. Number 1, if all the plotted value of rk against k are very near to 0, we may conclude that the given time series is an independent series. Number 2, if value of R1 is large and other values R2, R3 up to so on are decreasing respectively, then we may consider AR model as proper for the time series. Number 3, if the plotted values of Rk do not appear to be near 0, then the given time series is not stationary, but it may be of non-stationary type. Tests for stationarity. Now we understand that it is very important to know whether the given time series is stationary or not. There are many approaches that can be used for this purpose. We shall study some of them in brief. Number 1, Qstatistic. The statistical significance of any estimated rho k, that means rho k cap, can be judged by its standard error. Bartlett's has shown that if a time series is purely random, that means it exhibits white noise, the sample autocorrelation coefficients rho k cap follows normal distribution with mean 0 and variance 1 by n. From this, Qstatistic is defined as Q equal to n summation k from 1 to up to m rho k cap square, where n equal to sample size and m equal to length of lag. Q has chi-square distribution with m degrees of freedom. This was given by Box and Pierce. Here we can test the joint hypothesis that all rho k up to certain legs are 0. If chi-square calculated is greater than chi-square tabulated at chosen significance level, we can reject null hypothesis. That means at least some of them may be non-zero. Number 2, LB statistic. Jung box, that is LB statistic, is a modification for Qstatistic. LB equal to n multiplied by n plus 2 summation k from 1 to up to m rho cap square divided by n minus k, has chi-square m distribution and hence apply chi-square test as usual. This test is more powerful than the above Q test. Number 3. Unit root test. Unit root test, denoted by URT, is widely popular for its applications. Let us write Yt equal to rho Yt minus 1 plus Ut, where rho lies between minus 1 and 1. We denote it as equation number 1, where Ut is a white noise error term. If rho equal to 1, equation 1 is a random walk model without drift and it is a non-stationary stochastic process. From equation 1 above, we write Yt minus 1 equal to rho minus 1 Yt minus 1 plus Ut. Thus, delta Yt equal to delta Yt minus 1 plus Ut. We denote it as equation number 2. If we test the hypothesis delta equal to 0, that means rho equal to 1, we have a unit root and hence given the time series is non-stationary. Decay-Fuller test. Dickey and Fuller have shown that under the null hypothesis delta equal to 0, the estimated coefficient of Yt minus 1 divided by standard error is tau statistic. They have computed tables for DF statistic for different sample size. Tables are extended by Mackinnon, giving critical values at chosen significant level. Test is carried out as number 1. Regress equation 2 above for Yt against Yt minus 1 and estimate coefficient of Yt minus 1, that is delta cap. Obtain DF statistic tau by computing tau equal to delta cap divided by standard error of delta cap. Generally, this may be negative. Number 3. Find modulus of tau, that means absolute value of DF statistic. Number 4. If the computed absolute value of DF statistic exceeds the absolute DF critical value obtained from DF tables, reject the null hypothesis that delta equal to 0, that means rho equal to 1, hence time series is stationary. Number 5. If the value so obtained does not exceed the tabulated value, we do not reject the null hypothesis, hence the time series is non-stationary. Note that this test is also further revised as augmented DF test. Co-integration. Let us define DPI equal to real disposable personal income and PCE equal to real personal consumption expenditure. We take logarithmic values of these variables denoted by LDPI and LPCI respectively. Note that both the above variables have their respective time series. LPCET equal to beta 1 plus beta 2 LDPIT plus UT. We denote it as equation number 1. This is a very well known equation in macroeconomic theory. Beta 2 is the elasticity of real consumption expenditure with respect to real disposable personal income. We can call it as consumption elasticity. We write from equation 1 as UT equal to LPCEP minus beta 1 minus beta 2 LDPIT. We denote it as equation number 2. Note that both LPCE and LDPI series have unit root and thus have a stochastic trend. If we put UT for unit root analysis, we find that it is stationary. This interesting fact is called co-integration. Two variables will be co-integrated if they have a long-term or equilibrium relationship between them. Economic theory is often expressed in equilibrium terms. Here, equation 1 above is called co-integrating equation and the slope coefficient beta 2 is called co-integrating parameter. Thus, co-integration means that despite being individually non-stationary, a linear combination of two or more time series can be stationary. Co-integration between two or more time series suggests that there is a long run or equilibrium relationship between them. There are different tests like angle Granger, that is EG, and augmented angle Granger, that is AEG test to find out if two or more series are co-integrated. There is error correction mechanisms denoted by ECM given by Angle and Granger, which is a means of reconciling the short run behavior of an economic variable into long run behavior. Note, there is a very wide literature in respect of time series forecasting models, etc. Our study is kept limited up to this stage only. Thank you.